So for the third assignment, we will be doing floor plan optimization using NSGA II, which is a algorithm used to solve multi objectives. So here we have to design a chemistry workspace for IITGN. The workspace must contain three particular spaces. One is sitting space, one is laboratory, and the other one is equipment room. So the overall length and width are 25 feet and 25 feet cross 25 feet is the area of the total workspace. Our aim is to maximize the area and to minimize the cost procured to build a workspace. So since both are these conflicting objectives, since if we increase the area, we have to pay more price to build the same. So we have to increase the area in the sense that the cost should be decreased. So this should be our main objective overall. So now I'll show you the code that I have built to do the same. So this is the code for solving the multi-objective optimization. The objective function defined the objective function has been designed like this. This x1 represents the width of the sitting area in feet. Length of the laboratory in feet refers to x2. A1 is the area of sitting space. So this particular section is the width of the sitting space, and this is the length of the laboratory, which is x2, and this one is x1. So the area of sitting space would be 25 into x1, and area of lab would be 25 minus x1 into x2, area of laboratory, which we have to maximize, and the equipment area would be the total area minus area 1 and area 2. So we have to maximize the area of laboratory. That's why I have kept minus sign over here. So the algorithm will minimize it, but at the end we'll get maximized output from it. And the total summation of cost. So these particular cost factors are the cost per square feet of area pertaining to the sitting space, laboratory, and the equipment room. Now we'll see what are all the parameters that are included in the code. So we have two variables. One is x1, x2, x1 the sitting space width. The x2 is the laboratory length. The variable size is 2. The lower bounds for the x1 is 10 and upper bound is 15 feet. For x2 it's 10 and 80, which has been mentioned in the problem itself. So we have two objective functions. One we have to minimize and one we have to maximize. I have kept maximum iterations as 25 over here. Initially population I have kept as 300. The crossover probability, it is recommended that we should keep it high, so it's 0.8 as of now. And other like it, every variable, like each variable has been represented in binary encoded form. So 8-bit representation for every variable. So let's run the code up till here. So this hard limb, this particular line over here will give me a total representation of chromosomes, 300 chromosomes in a binary form for x1 and x2. So this particular matrix up till here, till 1 to 8 we have x1, from 9 to 16 we have x2, binary representation of an x1 and x2. So in the 17th column we will convert binary to decimal for the first variable, 18th column for the second variable, and 19th and 20th we will convert x1 and x2 according to the bounds, and which means within the bounds. So this binary to decimal conversion will give me a number between 0 to 255. So I'll use this operation to convert within the bounds. Once we run up to here, we get n matrix, which has both the variables along with their binary to decimal conversion. So now we'll give it as an input to the objective function, and we will get the output f, which is the cost and the area. I mean both the objectives. So this PO structure file contains x1, x2, position of x1, x2, along with f value. So it contains three fields, x1 and x2 are the variable decision variables, and f contains the both the objectives. Objective 1, this is this minus 141 is the area of laboratory, and 2.5 into 10 power 5 is the cost pertaining to build that laboratory area. So up till here we have got initial objective function evaluation based on x1 and x2, and now we will initialize the Pareto front one, which means the rank one members. So initially we'll keep it as null set. The Pareto front would be null set initially. The domination set would be null, and the domination counter will be 0. Now for the to check which all variables or which are fitness values. This is non-domination sorting. So which all fitness values dominate each other. So we have a domination check for that. So we'll run this for all 300 chromosomes. So we'll go step by step over here. So this I represent 1 to population size. This J goes from 1 plus to population size. So this S and T are the structure which has x1 and x2 values and their fitness value. This SF and TF represents the fitness values of the cell both. Now in this particular field for I equal to 1, we'll have this as our S and all these values will be our T. So we'll check for every S which all T dominates or uh, how many times the S dominates the total, other chromosomes. So here we see SF, if all SF is less than equal to TF. Here SF, all SF means both the fitness values is less than equal to TF, and also any of SF is less than TF. If this condition holds true, then we put that particular chromosome into the domination set, which means the set which contains the individuals that dominate T. This S is SF which dominates TF. So this TF will go on up till the population size. And if it's not so, it will go ahead. And if all TF, this TF is less than equal to SF and any TF is less than SF, then the domination set for J will increase by I. So we will store I in that domination set of J, and we will increase the counter for domination, which means number of individuals that dominate S. So there might be some fitness values which will dominate uh, the S value stored in the S, this SF. There might be many TF which may dominate this SF. So we'll give a domination counter increment in the domination counter for the same. And if we find out that DC is equal to 0, which means there are no individuals that can dominate S. So that particular individual or chromosome can be ranked as 1 because there is no other chromosome which can dominate that particular chromosome. So that will be stored in our Pareto front 1. And for other Pareto fronts, and which I mean rank 2, rank 3, rank 4 Pareto fronts will follow this particular protocol. So we'll again see, we'll have I'll run until here. So we check for domination counter. So over here, every chromosome will have a domination counter. Here we can see every chromosome have a domination counter. And when domination counter, earlier we saw that when equals to 0. If it was 0, then we assign rank 1 to them. And using this operation, those who are not in the rank 1, we are checking for rank 2, rank 3, rank 4 Pareto fronts. If the domination counter, for this operation, we decrease the domination counter by 1. And if the domination counter upon decrement becomes to 0, then we give that particular chromosome to the subsequent Pareto front. And the rank is allotted simultaneously. So through this process, we get our all Pareto fronts. So in this case, we have got 7 basically six Pareto fronts. So rank 1 Pareto front has 69 individuals, rank 2 has 131, and subsequently, and summation of all this is 300, which is our population size. Next comes crowding distance and sorting. The crowding distance basically does is the how much far is the neighboring individuals from the current individual. So it's basically a protocol in which we check for every Pareto front. We have seven Pareto front, so we will run a loop from 1 to 6 because seventh one is empty, and we check. Uh, so for the first Pareto front, we have 69 members. The 69 members over here. So this gives me size of one, and we will store the values of objective function in I1 and I2. So this I1 and I2, so it contains all the 69 chromosomes, the number of the chromosomes, the area of laboratory, and the cost fitness value of the cost. So now we give the crowding distance to it. So this is the equation or representation of how we assign the crowding distance to the particular individual, and this is being repeated for all the seven Pareto fronts. So now we get the distance matrix or array, we can call it, which stores the crowding distance for each and every chromosome. And one more important thing, that extreme for every Pareto front, the extreme for the first and the last we assign as infinities because both these points should be present in our Pareto front. Now we do the sorting process. Our end matrix is 300 cross 20. So this 21 column will contain the crowding distance, and 22nd will contain the rank of the particular individual. Now, so I have stored in the 21st column the distance, crowding distance, in 22nd column the rank of the particular individual, and I have sorted that particular column of distance in the descending order, and then I have sorted again with respect to the rank. Now we'll see how does the matrix n looks. So yeah, it has all rank 1 solutions, rank 2 solutions in a ascending order. The ranks are in the ascending order and the distance is in the descending order. So here comes a very important operation. This was the initialization. So how does the initialization work? Now we'll go for iterating loop. So we perform here a single point crossover operation. So since our population was 300 and our probability was 0.8 for crossover, so the crossover, the individuals that will go for crossover will be 240. This crossover represents a random arrangement of all the 240 members which will undergo crossover. So we run a loop for parent 1, the parent 2. This loop goes from 1 to C, C is n crossover by 2. And we see for the first element, cross 2 into 1 minus 1, which is first. The cross first element is 9. So the parent 1 would be 9. The parent 2 would be 49. So it has stored binary representation of x1 and x2 of ninth individual and P2 has stored for the crossover second element. So here a single point crossover means crossover position could be random integer 15, like bits is 8. So random integer, any random integer between 1 to 16 or 1 to 15, we can choose that particular point in this particular array. And if suppose this is a point, so we will switch over the this binary representation. We will swap it. Basically, swap operation takes place before this and after this, like that. So this child one will contain two. This will be divided into two portions. The parent one, parent two. So parent one, the child one will have a portion of parent one from first column to up to the crossover position column, and have a portion of parent two array from crossover position to the next from crossover position plus 1 to the 16th column. Similarly for child 2. So, and we will update our total matrix n. So our new population size will be different, which will also include the parent plus the child. So now our new population would be 540, which has also incorporated the parent and the new children formed after the crossover operation. Now we can go for bit flip mutation operations. So now with our mutation, the probability I have kept as 1% of the total population. So this operation takes place on the total population size, new population size, which is 540 as of now. So it will say that 6 random chromosomes will undergo mutation. So we'll find out which all chromosomes will undergo mutation. So this IDX gives me 184, 287, 106, and all the 6 will undergo mutation. Mutation bit flip mutation means that we get the binary representation of these particular individuals and we'll flip it at any random position. So if it suppose that position is 0, the representation of that particular bit is 0, then we'll flip it to 1, and if it's 1, then we'll flip it to 0. This gives a diverse solution and does not stuck in local optima. That is the main function of. Sometimes worse solutions might be in one generation, but after mutation, it can be a good solution in the next generation. So this avoids that particular sort of happening. So after mutation and crossover, we'll update the n matrix with like the similar operation that we had earlier. So now n matrix has become from 300 to 540 cross 22. So this stores all the individuals, and the similar process is repeated again for numerous iterations. This is crowding distance again, sorting. After sorting over here, since our population size is 300 and this n matrix is 540, so we have to select top 300 or the best fit 300 chromosomes out of this n matrix. So this n select does the same. This n select will give me 300 cross 22, the top fit or the best fit individuals or chromosomes which will go into the next generation. This members F1 gives me how many members are there in the front one. So this front one has 114 members. So this gives me the same. And just stores the number of front one members. And we'll similarly plot the graph for the same. So I have I'll run it again from the starting. And we'll see how the visual representation of Pareto rank 1 Pareto front looks over iterations. You can see the over iterations, this rank 1 Pareto front is changing. So after 4 iterations, we get decent rank 1 Pareto front. So the architect over here can decide that if suppose budget is of 2.5 to 10.5, what could be the area of the same. So this trade-off can be decided using this rank 1 Pareto front. So this has a non-dominated solutions. So here main outlook could be if we change, since this particular operation has been completed in 4 iterations, if I change the crossover probability to 0.1 with same population size and same mutation, it will take much higher iterations to solve the problem. Here we can see that earlier it was 4, now the iteration count is increasing. I've kept it as 25, we'll see till what number it goes. So it went up till 18. Also this particular, there are some points here, there are gaps on here. We can also avoid that if we increase the population size. It's recommended to keep higher crossover probability because it gives the result in much lesser time. So with increasing population size, it gives us the liberty that more individuals or more persons are searching for our solution, or the best fit solution. In the iteration of it's a very diverse solution. Now it's converging and giving us a perfect Pareto front over the time. And this is also visual representation for our problem, and we have successfully got a Pareto front for the same.